What we're going to do today is we're going to continue the Trig review, and this is after the class. The students aren't here anymore, but I wanted to make sure we completed these DVDs and the recordings so that there's a complete summary of the course in these review sessions. So this will be the third Trig review session, and on the second review session, the previous recording, I talked about the material called Applications of Trig Functions. This comes from in our textbook from Chapter 8. And what I did not have written down during that session number 2 on review was which recording numbers are associated with that material. So if you have the same textbook, in section 8.1, 8.1 is right triangle trigonometry. So if you're reviewing something with right triangle trig, then the recording, if you want more detail on it, which was on the previous review session number 2, if you want more detail than that, you can go back to recording number 16. If you're doing law of sines, and that was covered in session number 2, but if you want some more detail on law of sines, you can find it in our current textbook in 8.2. And the recording numbers are number 16 and 17. 8.3 is the law of cosines, and again in review session 2 that was covered briefly in a summary form, and the recording number for more detail on use of law of cosines is in recording 17. And then finally in this chapter is simple harmonic motion, and this is really an important topic in physics and engineering subjects, and more detail is offered back on review session number 2, a little bit of detail there, but then if you go back to the end of review session 2, if you go back to recording number 17, there's some additional information there. So what I'd like to do is to take and I don't think I want to go back over the right triangle trig or law of sines or cosine material. I think what I want to do is spend a little more time in this review session on the simple harmonic model, because that's quite important in application areas. So let's look at the way some textbooks, actually most textbooks, lay this out for simple harmonic motion. If we would take, the classic example would be to take something like a spring with a weight hanging from the spring. So if we would take a weight with a spring, and springs have some sort of stiffness to them, and if you hang a weight from it, the spring is going to extend a little bit. And then it's going to be sitting here in what's called an equilibrium position. Equilibrium position. If you would then take this and push, say, up to compress that spring a little bit, then you might push it up to, say, a starting position up here. So the spring would be compressed, and so let's say you do this and you start the spring here, or start the mass up here, and then you pull your hand out and let it go. Then what it's going to do is it's going to oscillate. It's going to fall, it's going to come back and pass through this equilibrium location, and this will be where it's traveling the fastest. When it passes through the equilibrium location, and then it's going to continue traveling downward until the extra spring force that develops in the spring wants to slow that thing down, overcoming the gravitational force. And so it's then going to start to slow it down until it comes to rest. Now it's going to come to rest. If it's what's called a linear spring, it's going to come to rest the same distance below equilibrium as it started above equilibrium. So this will be the end, or this will be the bottom of its motion. And I think you can see that that pattern is going to repeat itself. It's going to slow down and stop. It'll be stopped down here, and it'll be stopped up here, and it'll oscillate back and forth between those. Now, if we would say that we're going to measure a distance from this equilibrium position, let's call it, say, d, using the same symbols as our textbook, and this would be positive displacement. So the model that you see in the textbook would be d equals, and what we're going to do is we're going to actually start this thing up here at a certain value. And then it's going to oscillate down. And let's say that distance happens to be, I'll use the same symbol as our textbook does. Let's say this distance is A right here. Now, what you want to think about is the fact that this thing is oscillating up and down. So it starts up here, it comes down over as time passes, stops down here, comes back up, goes back down, and you can sort of get a sense, even though that's just up and down, you can sort of get a sense that that looks kind of like a cosine function. And so that would be a good way to model this. And so this would be cosine some omega t. So if we graph that displacement where this mass happens to be as a function of time, then it's going to start up here with some positive d, which d value equaling a at time 0, because you know that if I treat this as a function of time here, then d of 0 is a cosine of 0. Well, cosine of 0 is 1, and so it starts out with this y-intercept here at time 0, y value of a. And then what's going to happen is this thing's going to oscillate over time. It's going to drop down to where it gets as low as negative a down here at the bottom, and it's going to cycle back and forth through that. Now there's one cycle, here's a second cycle. Now we've learned earlier in the course, and this again is back in recording number 17, is we've learned earlier in the course that a model called a sinusoid like this has an angular frequency of omega. And the period of a cosine function that has a factor in here, a multiplying factor called omega, the period of that is going to be equal to 2 pi over omega. So that means if we've got this model built here, and we can see that this finishes one cycle in its period here, and so this is then 2 pi over omega. Half of that would be where it's going to bottom out at pi over omega, and this is going to be time, probably it could be in seconds or hours or whatever. So let's say it's in seconds, and then the amplitude is some other value. It could be in meters or centimeters or something like that if the spring is moving up and down over here. Okay. The time it takes to come to pass through its equilibrium position is going to be right here, because d would then be 0, which is the way we set this model up. So that's how you could then find, if you took half of pi over omega, you're going to have pi over 2 omega is the point in time where it passes through the equilibrium location here. Equilibrium location. And then it's going to continue on down, stop, come back up, moving fastest as it passes through the equilibrium position. So you can build a model. If you had the model instead, if you pulled this mass downward and started it down here, then you'd be starting it at a negative value. And you would have this graph turned upside down. It would be starting down here at the bottom, and it would be coming back, traveling upward, and then reaching its peak after half a cycle, and then come back down. So that's a simple example of simple harmonic motion that, like I said, you'll see that in physics, or you might see it in an engineering course. There's another important thing. If you want to know what the frequency is, first of all, think about what period means in the sense of time passing. The period is a certain amount of time. This could be something like seconds per complete cycle. It takes that much time to complete one cycle. Okay? So if that's true, then if we turn that upside down, find its reciprocal, we're going to have something we like to call oftentimes f. Some subjects in physics or engineering might use a different symbol for this, but this is then called just the frequency. If you turn the units of this period upside down, you can see that the units here now are going to be cycles per second. Cycles per second. And that's something we've all heard about. Oftentimes we abbreviate that just CPS. All right. Notice that if we would come back up here and let's see, if we would take this equation now and insert the period right here, look at what we have. If we take the reciprocal of the period, so we put in 2 pi over omega right here, then that's equal to, the reciprocal of this is omega over 2 pi. And then if you multiply both sides by 2 pi, we're going to see that omega is equal to 2 pi f. So what we could do is we could take that omega and we could replace the omega in the original model with 2 pi f times t. So if you came along and said something is oscillating at 60 cycles per second, you could just put 60 in right there, and you'd have 120 pi times t. And 60 cycles per second is what occurs when you're doing when you're using alternating current in this country, 60 cycles per second. So you'd have 160 in right there. You get 2 times that is 120 pi times t, and that would give you a nice model for the way alternating current occurs in this country, as far as its voltage goes. Now, watch what else we can do with this to make things a little more exciting. Let's say we have a harmonic model, and let's multiply it by something that is decaying. And a simple thing to do would be take maybe an exponential decay model. Let's say I took something like e to the negative 0.1 t, a tenth of t as the exponent with a negative sign. That's a decay exponential, and we'll draw that in a second here. And then let's multiply that by a harmonic model. So let's put a multiplier of a on there to change its amplitude from 1. And let's use a sine this time, omega t. And let's just call that y. So what we have going on here now is the following, graphically. Here's y, here's time passing. I think we all know that the sine function simply oscillates between -1 and 1. Up and down, up and down, up and down. Okay? That can't ever be any bigger than 1. If you multiply that by a, then that product can't ever be any bigger than a. At time 0, look at what happens here. At time 0, then we drop in time 0 here, and we have e to the 0, a times e to the 0, times the sine of 0, and that happens to equal 0. Now, what if we wanted to be up on a crest? In other words, where the sine value takes on a value of 1. Sine omega t can equal 1 at some point in time. So let's solve that problem. We know that this angle in here has a sine reading of 1 when that angle is pi over 2. So omega t could equal pi over 2. Or, as you know from a sine wave, it occurs every period then thereafter, won't it? Every period thereafter. So if we added to that the period 2 pi over omega and put a multiplier on it like we've done in other things earlier in the course, then this would be finding the values of time at every single location in time where the sine reading becomes a value of 1, its maximum value. And that, you can see, will occur at pi over 2 omega plus 2 pi over omega squared times k. Now what I want to do is to see what happens when we multiply that by this exponential. So let's see what happens now. If I drew this exponential without the sine wave in here, then it would be a decay exponential because of the negative exponent, and it would be coming down from an initial value of a. So it's going to be something like this. And the negative of it would be down here, looking like that. Now what's going to happen is this sine wave is going to be, its force, we found its initial value of 0 here. And then this sine wave is going to oscillate with the same period as we described previously. And it's going to continue damping down like this. This could be thought of as a simple, a pseudo-damped oscillator. The period here, again, is going to be occurring at 2 pi over omega, which means that this point at the crest right here, the crest of the sine portion of this is going to be occurring at pi over 2. No, I'm sorry, pi over 2 omega right there. And then every crest should be occurring periodically thereafter. Let's see. Yeah, I think the mathematics here is okay. What I want to do is let's just spot check this spot right there. And actually we'll be able to check this in a minute on the calculator. So what we could do is let's come in here and let's just say we're going to put in a omega value of, how about pi? Let's let omega equal pi, just to see where this takes us. If omega equals pi, then our model is going to be y equals, and why don't I put a value in for a, just so we can probably kick this into the calculator in a minute. Why don't we say this is a value of 2? And so we're going to end up with 2 times e to the negative 0.1 t times the sine of pi t. So what I want to spot check is the calculation that we did up here previously. If we use our omega value of pi, then this thing is going to equal the places where the crest occur would be occurring at pi over 2 times our omega. And I believe that this is going to be correct. This would be over pi squared times k. And so we clean that up. And so a crest will be occurring at a half a second. And then it should be occurring at 2 over pi. Let's see. No, actually, I did make a mistake up here. So let me back up here for a second. Remember, the period is just time. And what we have here is omega times that. So what I technically should do here is this should be a k multiplier on the period. A k multiplier on the period. Now I did indeed place 2 pi over omega in there. So this is momentarily puzzling to me, but I'm just going to live with it. I'm just going to leave it this way. And then what's the period of this model? The period of this model is 2 pi over omega, which is 2 pi over, we're using pi for the omega reading. So the period is 2. Ah, there's the fix. That's what I was needing. So if these units now are in time and seconds, then we have a period. We have the first crest occurring at a half a second, and then the other crests are going to occur as multiples of 2 times k, an integer, added to that. So this first crest is going to be occurring at 1/2 a second. and then the next crest is going to occur 2 seconds later. And so that would be at 2.5 or 5/2 seconds right there. So what I'd like to do now is to show you, you can think of this as a damped oscillator, and I believe what we could do is go ahead and kick this into the calculator and pick up an image on the screen here. I'm going to put the calculator in radian mode. We are in radian mode. We go to y equals. And we're going to go ahead and put this model in, and we decided to use an A value of 2. And we're going to multiply that times the decay exponential. And then we'll multiply that by our sine function with a pi omega value times x. So there's our model. Now we want to set an intelligent viewing window based on those values of time that we specified a moment ago. And so I think I'm going to let this thing run for maybe about 6 seconds, 0 to 6 seconds. And let's put tick marks every quarter cycle, which looks like every 1/2 second. And then let's vertically, we set A up as a value of 2. So let's go ahead and set this up so that it's say a -2 to 2, and put tick marks every 1. And let's see what happens. Now before I hit graph, I have a little bit of concern about what I used here for this exponent. This may cause, without me thinking about it too much, it may cause the decay exponential to be a very gradually decaying exponential function in the scheme of things. So without thinking about that numerically, I'm just going to go ahead and blindly try it based on that window, and then we may come back and alter this multiplier here to make it look a little nicer. Oh, this is feeling pretty good. So what we can do once we see this, and you can see that it's not coming down very quickly, what you could do if you want to is you could put 2 times the exponential down here as a separate function, and that's going to show you, and then we also could put the negative of it. And so this, let me just illustrate this, and we can put the negative of the y2 function. We can get that function by going to variables, y variables, function, and select number 2 right here. Say that again, variables, y variables, function, and then item number 2. It puts it right there, so it's going to draw the decay exponential from above, and then it'll turn it upside down and draw it as well, and lay it on top of this model, the damped oscillator. And you can see now the envelope at which this model, this damped oscillator, is just touching. Now what you can do, what's nice about these calculators is you could come in here then, and I could make this damp down quicker by making this number a little larger. Like let's say I made it a 0.5 right there. Now watch this. Doesn't change the periodic character of the function at all. All it does is just makes it damp down quicker. Similar to what a shock absorber might do in an automobile. You'd want it to damp out the bump you just went over rather quickly and not sit there and bounce your way down the road. Okay. The boundaries a function, an oscillator is in like that are called an envelope. And you could have a quadratic function that was an envelope. You can use exponentials like this. You can have something grow. Instead, all I'd have to do is to make this a growth exponential is just take the negative off of there, and now we're going to have something that's going to become unstable. Whoops, sorry about that. Let me expand the y values on the window. I expanded the y values on the window, and now watch this oscillator go. So now you have an unstable situation where your motion is growing over time. And this could be, this is an illustration of a situation sometimes that occurs called resonance. Earthquakes, buildings will sometimes start to shake, and if you excite what's called their natural frequency, the amplitudes continue to grow until the object becomes unstable and fails. All right, I think that is plenty on that material. That was a little application involving harmonic models, and so we'll end this segment and then we'll go on to polar and vectors in the next segment.